And this is a forum we have at 1:30 on every Tuesday that the classes are running. And it's been a lot of fun. We have people from all over the valley and all over the world come and speak. Before I get started, I'll just mention that we are on Adobe Connect, and some of the people will be watching from all over the place, and they might ask a question. If you are one of these people out there, please, just send a message of a question to me, and and I'll try to ask it for you. We look for TOCS and CMU, and you can actually see all of the talks just about that we've given here online. So without further, and the class will go from kind of now until 2:25, and then we have soda and some cookies in the hallway, and you can meet a little bit more. So Subhasish is a professor at Stanford, and I was introduced to him through a very amazing and exciting electrical engineer that used to work with me at IBM, one of the most inventive people I know, Dave Yalou. And he just thinks about all sorts of uncertainty in creating the infrastructure. Often it's the hardware, really, that can be an interesting place to be. He was in Intel before he went to Stanford. He's got 15 graduate students in his laboratory, and they work on everything from fault tolerance and error detection in big chips to actually thinking about what can be done to replace the MOS chips of today. So without any more ado, please, Subhasish.
Thank you. And this is really an honor to be here. And as Ted said, through one of our friends, I got to know him, and I always tell him that I'm a big fan of the track point. And my friend has a theory that why I would, be a big fan of the track point. But what I'm going to do is that I'm going to talk about robust system design. That's what we do in our group. Now I understand that this presentation may be skewed a little bit, but the one over there on the wall, it looks very nice over there. So feel free to, okay. If something doesn't show up over here, you can see it over there. So of course, my students and collaborators, they did all the hard work, and I just have the fun to be here and sharing our results with you, and I'm looking forward to a lot of interaction. So please feel free to stop me and ask questions. As I always joke, this is a reconfigurable presentation, which means I do know which slides to skip if I run out of time. So I would rather have a good conversation than just having a one-way traffic. So our society depends a lot on electronic systems. There is no news over there, but unfortunately, malfunctions of electronic systems have a huge impact on all our lives. And these malfunctions can go all the way from some annoying crashes, loss of data and services, all the way to very serious problems that we deal with. So here are a few examples, and I would like to call out one of these. This is a transportation example. What happened was this was in 2009, end of 2009. What they really finally found was that there was a single circuit board in the whole aviation control system, and a single circuit board produced an error in a single cycle, and that took down a large part of the network, and hundreds of flights were canceled or delayed all across the US. Now, isn't that amazing, right? So just one thing happening, it was a small circuit glitch. That's what caused the error, and that brought the whole system down. So that's the kind of level that we are talking about over here. So if we look at how to build systems and how to build robust systems, of course we want to avoid those kinds of failures that I was just talking about before. So I did a little search and found that robustness had always been the key system design objective. So there is nothing new over here. Edison actually talked about design bugs, and his point was that like when you have an invention and, from the invention to an actual product, bugs are the things that you have to worry about. And he talks about that in great detail. I found out it was interesting that, the Z3 computer that they had, and they chose relays as the switching elements for reliability purposes. And, we have a project on nano-electromechanical relays, and, I was digging through the history, and that's what I ended up with. And if you look at the ENIAC computer, it supposedly had one tube failure every 2 days. And even for a computer of, it was not a very super complex machine, it took them 15 minutes to actually go and find which was one of the tubes that was not working, so that they could replace it and keep it going, basically. So that's, what's going on in the history. So if you look at, what are the things that are really difficult and getting more difficult moving forward, there are 3 things. You have to worry about complexity, because today's test and validation methods can barely cope with the complexity of the chips today. So moving forward, one needs new ways to make sure to minimize the effects of defects and design flaws in future complex chips. So essentially, these are design bugs that could be made by designers, that could be made by incorrect interpretation of what people think about specs, and these specs are not just behavioral specs, but these are also electrical specs of a design. And we'll talk about that more. This is getting really difficult. The other thing that's getting very challenging is CMOS reliability. In the past, people that were working on space electronics and military, they would worry about things that the commercial people would almost never ever worry about, unless you were building very high-end systems such as the mainframes and servers and so on. Unfortunately, what has happened is since 90 nanometers, a lot of those failure mechanisms that were largely benign in the past, or people would not ever worry about when building a kind of a mainstream commercial system, those failure mechanisms are becoming visible at the system level, which means that now when you build, for example, 15 nanometer microprocessor or networking chip, you have to worry about not only the fact that you could make design bugs, or there could be errors because of incorrect interpretation of electrical specifications, but also you have to worry about the fact that a transistor has its own mind, and sometimes it would just decide to flip a bit. Or the transistors are like human beings; they age over time, and the amount of aging depends on how much the transistors were stressed during their lifetime, and all these physical effects become very important, at those technologies. And if you look at, beyond silicon CMOS, so silicon CMOS is the mainstream technology that we all use today for building our chips, but we are not that far from the end of the roadmap. I know that every time people said that they were proved wrong, because human beings are very creative and they have ways of doing things, but it seems like this time it could very well be true. In any event, for various reasons that have to do with power and performance and so on, people are very the industry as a whole needs new materials to create the next generation of switches and transistors. And the question is, does it really matter what you want to do if you look at all those candidates? Inherently, those candidates have substantial variability and imperfections, and we will talk about that too. So given all this, there are lots of uncertainties in future design, future hardware design. Uncertainties could be because of the fact that there is no way to completely verify that these things will actually work. Even if these things were completely verified, still the underlying physical realizations, they would have reliability problems much more than ever before. And as I said, beyond silicon CMOS, inherently they're imperfect. Given all that, the question is, how do you build systems that perform correctly, even in the presence of this enormous complexity and these increasing underlying disturbances? So that's the focus of our research in our robust systems research group. Now the question is the following: so what's new about all this, right? People have been talking about design verification for a very long time. There is a whole field on fault-tolerant computing. And people always look at new materials, and they have been very innovative in creating complex systems out of new materials. So what's different now? So I think this slide captures what's different now. I would be happy to substantiate my claim, but I would say that existing ways of doing things are either they're very inadequate, so you're not going to get enough benefits, and B, they're very expensive, and I'll give you examples of that. So for example, if you look at design bugs, typically if you talk to a designer, the designer would say that the way to deal with design bugs is to do what is called pre-silicon verification. And there are many ways of doing pre-silicon verification. For example, running a lot of simulations, formal verification, and all that. Tomorrow, or even today, where the focus has to be is not on pre-silicon verification, but this thing what is called post-silicon validation. And we will talk about that. Similarly, if you look at reliability failures, traditionally, the commercial electronics would try to avoid those reliability failures so that they never had to deal with it. Versus tomorrow, even your mainstream systems have to be able to tolerate those reliability failures. And since these are not high-end servers that can pay a 40 or 50% tower price and charge that much money from the Wall Street to make up, you have to tolerate those reliability failures at a very low cost. And this is a very difficult problem, and we will get into that. And if you look at materials beyond silicon CMOS, typically if you talk to some of my friends in chemistry or physics, they would be telling you that they can solve all problems by playing materials games. And actually they have done amazing things. The only trouble is that at that nano scale, we are talking about things, these carbon nanotubes that I will be talking about, their diameters are between 1 to 2 nanometers, right? And hopefully one day if we get enough density out of those carbon nanotubes, the intercarbon nanotube distance has to be somewhere around 4 nanometers or something like that. So at those scales, there is almost no way that you can go and print something very nicely and then create some substrate. So you have to deal with inherent variability and inherent imperfections. And as a result, a lot of these problems do not get solved by materials alone. Actually, the way to solve those problems is by design. Actually, and this imperfection immune design that I'm going to talk about, that actually goes and works with the materials in the right way. And then suddenly, a problem that could not be solved only at the materials level gets solved very easily, almost trivially, once you know how to do it. So let's get to the core of the presentation. So first, I will spend a little time talking about how to deal with the complexity and detecting and fixing design bugs. And this is where I will focus a lot on post-silicon validation. So as I said before, so this is a typical, very simplified design flow. In real life, design flows would have a lot of loops. And this is a straight pipeline that I'm showing over here. But essentially, you do design, and then you will be running a lot of pre-silicon verification and formal verification and all that. A lot of simulations and formal verification and all that. And then when you think that your chip is a good enough chip, you just send it to the fab. The chips come back. You go through this phase which is called post-silicon validation, and that's when you go for high volume. That's when you make money. Now, typically, a lot of time and effort used to be spent over here in the past, versus now, a lot of time and effort is being spent over here. And that's given by two of these examples. So AMD, Barcelona processor had a bug in their translation leukocyte buffer, the TLB. And it took them, as a result, it resulted in a 6 months delay in the shipment. And 6 months is a huge number, as we all know in this industry, because you could just simply not hit for example, the Christmas market. Similarly, there was an Intel vice president who gave a keynote speech, like a few years back, and he talked about how this post-silicon cost and complexity is rising faster than design cost. And I have seen some numbers in the industry from various companies on, if you look at how much resources are being spent in design versus how much resources are being spent in this validation, actually the balance has already been tipped. You spend more time in validating stuff than designing the thing. So that's where we are. So what kinds of bugs you got? So as I said, there are two kinds of bugs that you have to worry about. One are the so-called logic bugs. Essentially, somebody just coded the Verilog wrong, and simply because either it was a goof or it was because somebody didn't understand the specs properly, and so on. But then there are these bugs that happen because of the interaction between the design and voltage, frequency, and temperature corner. So this particular chip would be working fine, at room temperature, but only when you run some certain workload and then the chips get hot. That's when this particular chip doesn't work. Now, how in the world is somebody going to go and find out what's going wrong? And in the nomenclature, they also call it Heisenbugs, because when you try to observe something, probably the state of the system would be changed, and you cannot even see that the bug was happening anymore. So this is very typical. So here is a chart from one of my collaborators at Intel, which shows some graphs. Don't ask me why there was a dip over here. Everybody asks me, and I do not know the answer to that. I should go back and ask them. But essentially what it's showing is that, so this is essentially logic bugs versus electrical bugs for some products, some line of products inside Intel. What it's essentially showing is that if you look at the number of logic bugs, that's of course going up with generations. But typically, if you had a logic bug, it would take a week to find out what the problem of that bug is, and so that one can actually have a way to fix the bug. Versus if you look at electrical bugs, they are really rising because of, again, process uncertainties. And as a result, it would typically take a month to figure out what the problem is to fix it. So there's a huge problem over here. And a product does not have one bug. Like a product has a lot of bugs. So now you can calculate how many man-months would be needed to deal with those bugs. And that's where the costs of post-silicon validation are coming from. So here is kind of a cartoon for what people do in post-silicon validation. So when the chip comes back from the foundry, they would plug it into an actual system, and they would run all sorts of tests. And I literally know of people that play games basically on these chips to exercise those chips. So run on boot operating systems, play games, run functional tests, and so on. And if they are lucky, they will see this blue screen of death, right? If they're not lucky, their customers are going to see the blue screen of death. And now just think about yourself sitting in front of this blue screen and trying to figure out that these hundreds of millions of transistors, which one of them just produced something incorrect within like a couple trillion of cycles that you ran this particular chip, right? That's what is called bug localization. That's when you figure out that, for this particular chip, if you focused on this particular design block, maybe, like at cycle, 1 million, whatever, this particular design block produced a problem, and that essentially ended up, showing up as a blue screen. And that's what is called bug localization. And once you localize a bug, actually, there are many interesting tools that the industry has created. For example, photon-based imaging, laser probing, and so on, where they actually can go and pinpoint what the source of the problem is, and and they can fix it. So the biggest cost over here is going from this blue screen to be able to tell where in the chip is this problem happening at what point in time. And this is called bug localization. That dominates the cost of post-silicon validation. So let's look at why that is the case. Well, there are multiple reasons for this. First of all, internal node access is a big problem. By the way, this was the Harvard Mark II computer, and supposedly this is the computer that had the first instance of a computer bug, because literally a bug was stuck in a relay basically. And if you look at the historical documents, it would say that's where the word debugging came from basically. So as you can see, this lady, she could access those relay panels, and figure out what the heck is going on. Versus this is the Intel Core i7 chip. I should get probably the Sandy Bridge now over here. This was like almost 2 years back. 700 million transistors with only 1,000 pins. So you got a huge access problem. You cannot look inside the chip. That's the first problem. But then there are some other problems. The other problems are the following. So typically, how do you debug a program, right? If there is a problem, you try to reproduce the problem, right, with some parameters changed to kind of pinpoint where the problem is coming from. But as I said, most of these problems that people in the hardware world deal with, they are Heisenbergs. So failure reproduction is a huge big issue. For example, you would have asynchronous IOs, and as a result, maybe the IO packets didn't exactly quite line up at the right time, so you may not be able to reproduce the bug. And even if you could reproduce the bug, typically what would you do? So whatever the system is producing, you run some sort of a simulation of the system to find out what the system should produce, and you kind of try to compare, right? The trouble is that a full system simulation, is like can simulate 1,000 cycles per second, versus a real system running at a gigahertz runs 1 billion cycles per second, right? So there is a million order of magnitude, 6 orders of magnitude difference over here that you have to cope with. By the way, if you're wondering what this is, can anybody guess what this is? This is actually a very high-end post-silicon validation platform that my Intel friends shared. So the chip, that was being debugged, you cannot see it. The chip is sitting somewhere over here on one of these boards. And guess what these windows are for? These windows are actually, each of these windows correspond to logic analyzers. So all these logic analyzers using all these cables are collecting data, and somebody will be doing a full system simulation to be able to debug. Now this is not a like a typically the first thing they would not use this platform as the first thing. They have smaller platforms. I just want to clarify that. But oftentimes they would have to go to a platform like this to be able to debug. So that's what we are talking about. Okay. Now if we can do something where this whole thing gets moved into the chip and takes 1% of the chip area.
This photograph is circa what year?
I would say around 2005, 2006, around that time frame. So it's not that far, Yeah. And actually, I visited several labs of several companies, and I have seen, stuff like that. Yeah. Okay. So what I'm going to show you is that, I hope that I motivated you that this is kind of an important problem to solve. So I will show you a combination of techniques that we are working on, which we call QED and IFRA. I will spend more time on QED. So I always have fun, telling my students that, like we have to solve this problem, and oh, by the way, you have to solve this problem without using any failure reproduction and without using any simulation, because those were the big problems we talked about, right? Now somehow, if we can show some interesting results where they're not allowed to use any of these things, which means that in real life, people will be using failure reproduction and simulation, but hopefully the results will be better, right? So what we will show you is that we can detect errors we can detect bugs very quickly, and we found that we can improve this by 6 orders of magnitude. I'll share hardware data with you, and we can improve coverage as a result of that. And is this practical? Yeah, because I will show you some results from the Core i7 hardware platforms. And also, we had been very fortunate that several companies, you just name, they have shared their actual logic bugs with us, basically on their complex SoCs. And because there was a lot of disbelief that, whether we could do what we were claiming we could do. And I will show you some interesting results on that. So here is the big problem that's happening. So we kind of probed a little bit to try to see, what's the source of all these problems, and this is what we found. Typically, what would happen is that when you would run some sort of like for example, you would play a game, right? Like run some sort of a test. Typically, at some point over here, there would be the bug will create some sort of an error inside the chip. And then after a very long time from this point, you will see the blue screen. And this is actually what is also referred to as error detection latency. And for those of you, that are kind of familiar with fault-tolerant computing, this is a very, standard terminology of what's really going on. Essentially, if this error detection latency is very long, it's very difficult to go back to the history and to be able to figure out what the heck was going on inside my hardware. Versus if this error detection latency was very short, hey, like I almost have my context when the problem happened, and I should be able to figure out much easier. And typically, what people do is that when people build chips, they actually go and invest real estate for debugging. So for example, they would put in things like memories on the chip just for debugging purposes, and this would be called trace buffers, for example. And they can trace maybe 1,000 cycles or something like that. So if this latency is less than 1,000 cycles, you will be doing fairly well. Like the kind of the relevant information will be already recorded, and and you will have a very good idea about, like what the heck was going on inside the chip, versus if this was 10 billion cycles, there is no hope you can do anything. Now let's look at what are some of the important bugs that happen in real life. So typically, this is what would happen. As you all know that, we are all using multi-core chips, and there will be more and more cores. But, interestingly, the bugs do not happen in the cores, because the cores that people use to build these multi-core chips, they are not problems, because these cores are reused a lot of times, so they are fairly well verified and so on. And by the way, the cores actually occupy a very small part of the chip. I shouldn't say very. They do not occupy the majority of the chip. So if you take a chip, first of all, a lot of the chip would be memory. So if you take off the memory, and then you have the logic. And if you look at the cores are not the biggest chunk of the logic. The so-called uncores, Intel calls it uncore, IBM calls it the nest. All the cache controllers, memory controllers, network controllers, and all that. Those are the ones that take up most of the chip area, and those are the ones that are the most complex things, because you are integrating stuff, and you have to do it kind of on a chip-by-chip basis, and you do not have a lot of time to verify that those things will actually work. So let's look at a typical bug. So for example, I have simplified this whole thing. Over here, let's say some core was running something, and then at some point it was writing to the cache, and the cache controller had some weird bug. And as a result, let's say this particular memory location, either didn't get updated. Essentially, the way it shows up is that some particular memory location gets erroneous. And after a very long time, maybe some other core will be trying to use that memory location value, and then after a while, it will get into a live lock situation, and there is a problem, right? That's a typical debugging situation. Yes.
Just say a little bit what's live lock.
Yes. So the way it would be live lock, would be the following. Essentially, there would be some sort of a variable basically, and on that variable, it's going to go and say it will try to grab something basically from somebody else. And once it grabs something from somebody else, that asks for something else, and it goes on and on and on. Now, if you look at if you talk to people, they would say, oh, you know what? I know very efficient ways of finding live locks, and there has been some really interesting work on that. Where people would be doing some sort of a graph matching kind of a thing on a chip, and all that. But the trouble is that even if you found the live log very quickly, that's not going to do much, because that's where not the problem is. The problem is over here, because there was a bug that happened somewhere over here, and after a very long time, this particular core is seeing the effect of that. Now, you have to understand this is a much simplified situation. In real life, what would happen is that these bugs will keep hopping even between various cores, and then it will finally show up at some live lock situation. Here is another example. I was visiting one of these companies, and they showed me this problem. What happened was they had a network processor that they built, and when the chip came back from the foundry, they plugged into the system, and then they suddenly found that the packet drop rates were just going through the roof. See, look, things were going fine, and suddenly the packet drop rates would just go so high, and suddenly after that, the system would either crash, or it would just hang or something. And they were like, oh, what the heck is going on? There must be a problem in our high-speed interfaces, because that's why maybe the packet drop rates were just going crazy, because of CRC checks and all that. It took this company, and by the way, this is a very well-known company. They have very good methodologies for verification and all that. It's not that they didn't do good verification and stuff. It took them 6 months to figure out what happened was that actually that the protocol that they implemented inside the chip, that had a bug. So it had nothing to do with high-speed I/O interfaces, electrical problems, or anything. It was a logic bug, and that logic bug was getting exercised only for certain corner cases. And as a result of that, when it was getting exercised, it would produce some small problems inside the chip, which nobody knew about. And after 10 billion cycles, okay, on the x-axis, that's when this problem would pop up, and the system would just hang. And these are the kinds of problems that we're talking about. So we had been, thinking about it. So how to solve this problem? And I had some ideas my students didn't like. I always, joke about this. And my students had some ideas I didn't like. And then we realized, we said, okay, you know what? If this is such a difficult problem, let's try to redefine the problem. And what we are doing, yes.
So the bug that you showed 2
Yes.
slides back, and now even this one.
Yes.
So even if you do verification like model checking, you might get the bug, but you're saying that the counterexample trace is going to be
That's
really,
right. That's
really
that's
long.
that's 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 right.
And the gap between the final event that caused the violation and the actual cause is far. Do you know whether in this industry people have done causality-like analysis to localize?
So I do not know the direct answer to your question, but I can tell you from what I hear. So there are two aspects to it. One is in pre-silicon, and the other is in post-silicon, right? Now, if you, for example, not that wouldn't work for this particular example, but if you had a smaller block, for example, where you could simulate, like using some high-level, design or something like that, you could potentially say that, okay, since I have everything observable in my pre-silicon environment, I could actually cut this down. Literally, I could go and check at every cycle, for example, right? Now the trouble is that, so for example, we work with some of these companies that build complex systems. When they run their high-level system-level tests, they abstract all that out because being able to check all those things is a nightmare basically, because you do not have all the capacity to do that, and they do end up with this very long latencies. That's what I have been told. Now, when you go and try to do the like kind of debug diagnosis kind of a thing, you might be able to use some sort of a causality. I cannot point you to a tool that that is the tool that does it. But I would be surprised if people wouldn't do it at all. So what we are doing is the following. We are actually changing the tests. So this kind of goes back to my background in fault-tolerant computing. I said, oh, you know what? This is a problem of error detection latency and nothing else. And in fault-tolerant computing, actually, you have a similar problem. You want to detect errors very quickly because otherwise you cannot recover from those errors. Because if you had a billion cycles, your stuff has gone to your network and all that, and checkpointing and recovery is very difficult. So we kind of took inspiration from that field, and we said, okay, like when I was at Stanford as a student, we did this work on software implemented hardware fault tolerance, which, by the way, my understanding is that NASA and many other places use now. So we said, okay, why can't we do the following, where we will take these existing tests, for example, their games and all that, and we will transform those existing tests into new tests that we call QED tests, and this by passing them through some mathematical transformations, which guarantee that you have the error detection latency to be bounded. Essentially, these are like self-checking tests, but the self-checking is done in such a way that it's not just simply self-checking, checking against itself, but also it's self-checking with bounded latencies, basically, and you create an estimation of how that latency could be bounded. And there are actually a very wide variety of transformations that you can use, where you can even apply some sort of ideas from design diversity and so on to create these tests that would exercise the underlying hardware in different ways and then very quickly detect these problems. Now, some of you must be thinking, oh, that could work for example, transient errors and things like that. How would that work for design bugs? So let's look at some numbers. So this was actually an Intel Core i7 platform that my Intel collaborators brought to our lab. And this platform was very unique because they opened up the entire platform so we could go and do stuff inside the chip. These chips are all unlocked, So I joke, I say that, my grandchildren will probably have to pay Intel money, like if there is a breach of trust over here. So, this is, there is a debug interface for this, through which actually the Intel engineers, what they did is they actually went and created electrical bugs inside the chip by changing the voltage and frequency. And then the question was, can you go and find these bugs? And this is what we found. So on the x-axis, we show the error detection latency. So with the original tests, and these tests were the ones that were selected by the Intel engineers because these are the tests that they would run to characterize their chips, you typically see that the error detection latency would be very long, billions of cycles. Versus over here, with this QED or the quick error detection technique, we could cut down the error detection latencies very significantly. Actually, you see a number which is 10,000. Actually, most of our error detection latencies are less than 1,000. The reason we had 10,000 is because for this particular system, we had to instrument the whole QED in software because this was already a done chip. So we could not add any hardware. And in the software, there were some C libraries inside which we could not go and instrument QED, and the C libraries took a long time to run. And as a result, there were very few cases with 10,000 cycles of error detection latencies. Typically, we would cut it down to less than 1,000 cycles. And at the same time, it's no surprise once it is done that actually, since we detect those errors so quickly, as a result of which the coverage also improves. Because if you had a bug, that bug can get masked later on, the effects of that bug. And now, since we detect those bugs so quickly, the effects get exposed much quicker. And on the hardware, we could find that our coverage went up by 4x. So we could detect 4 times more bugs than the original tests. When we were doing all these things, there was always a question about, hey, is this true only for that particular platform, or maybe there was some weirdity of that platform? That's not the case. So we also had access. Actually, we have another Intel system in our lab, which is the latest Intel 48 core system, right? So what's shown over here on this graph? So if you count the number of squares, it will be 48. So these are like 48 processors basically, and we are showing some sort of a shmoo plot at a particular voltage and frequency point. What a shmoo plot does is that if it is green, that means it works. If it is red, that means it does not work. Essentially, that's what a shmoo plot does. By the way, as you can see, that all these processors are nominally the same processors, but because of process variability, all these processors do not behave the same way at all these at this particular voltage frequency point, and you see more of that moving forward. But some interesting points over here. So, for example, if you look at this particular point, this yellow point, this is a really problem point. If you ran your original tests without the QED, what you would get over here is a green. But if you run the QED tests, what you would get over here is red, which means that you got coverage improvement by doing something like this. Similarly, over here, if you look at the purple points, something similar. If you didn't have, for example, output checks, and oftentimes, especially when you play games to do post-silicon validation, you cannot have output checks. And as a result, you would have these points to be green versus they will become red with the QED checks. And by the way, QED does not change the legal flow of a program, and as a result of that, it's not adding some illegal execution or something that you would worry about false positives. And finally, these were the points, for example, where the original test would crash after a very long time, but the QED test would find the problems very quickly. Yes?
I mean, I don't know this area very well. Yes. Are you instrumenting the system so that it's like runtime checks?
Yes.
Some checks are being done, and some of them are indicating whether.
That's exactly. Yeah. So essentially, I'm embedding the runtime checks through programs, but I don't have to do only in software. For example, if I could spend a little cost in hardware. By the way, for these systems, we could not go and change hardware at all because these were already built. We could even do it far more efficiently.
Right, and for that, why? I mean, there are many possible runtime checks.
That's exactly correct. So I'm glad that you brought up. So the question is the following: that there are many ways to do runtime checks, for example, right? So you can have assertions, as a classic example. So if you have assertions, the trouble is the following. So if you have an assertion mining tool, that would give you the zillions of assertions. And your question is that, hey, how do I pick which assertions to choose? And if I do not run the right assertions, I would not be finding the things. So what we do is that instead, so we take the fault tolerance route. What we do, we say, okay, we are not going to rely on those assertions. What we will be doing is that we'll be running some snippet of the execution, and then we will be rerunning the same snippet of execution in a different way. And then we will be, and if you have the snippets, I would be checking the results at the outputs of the snippets, and they should match. So in principle, what we are doing is an assertion, but in another principle, what we are doing is not what traditionally people would call assertion. So we do not have the problem of picking and choosing whether you check for this property versus that property. We check for all properties. Our tricks, our bag of tricks are in how you create diversity, so that you do not run into the same problem in the same way and detect these bugs basically. Go ahead.
Love the idea of diversity. I'm still confused about this assertion because
yes.
I picked a snippet of code. I mean, that snippet of code only used cache. It didn't do anything else.
That's right.
So it's not going to test any of it.
So
does anything.
So that's a good question. So what Ted's So what Ted's question is the following, that, hey, if my original test did not have coverage, my new tests are not going to have coverage either, right? That's the point. But that's not the problem, actually. So these companies have a huge coverage content. So running tests is not a problem.
I see they've already done that.
That's it. Well, there are still issues about how you quantify coverage, because they oftentimes they run redundant tests, and they do not exactly know, whether some test is redundant, and they didn't have to run it, just because that takes up resources too. So there's a huge issue there too. But so far as content is concerned, there is a lot of content out there that they can run. Their only trouble is that most of the time is spent in debugging, and if they're spending so much time in just trying to do debug, they do not even have enough time to run more content, because they're spending time trying to fix problems. So if you can cut down the debugging time very quickly, they can run much more content, and that would be even better, because the quality of their verification will go up. So what this is doing is, it's saying that you have enough content. Now let's try to see how we can nail down the source of the problem very quickly, so that you don't have to run too long, and you can debug it very quickly, so that you have more time to run tests.
So on the concrete example you had a few slides back,
yes,
you would detect that quickly.
Yes.
Because
that's a good question. Okay, let me go back.
Yeah, that's either this. Or
yeah, let's this one. So what we will do is the following. So when these codes would be running basically, so they would have their own self checks basically, re-execution and checks, and there are many ways of doing that, as you know. But that itself would not solve even the problem, because what would happen is that still, like something will be sitting over here, and then once it is transferred, that's when. So you have to use the principles of fault tolerance and apply something like scrubbing, right? Which is like proactive loads and checks. So now think about, you have instrumented this system where you have self checks going on in the cores themselves, and in all the encore components that are, have almost everybody has some sort of a memory that they write to basically. So you have this very fine-grained scrubbing that's also going on concurrently. And those are some of the places where we optimize that, when to scrub, when not to scrub, because, you do not want to do so much scrubbing that your original test flows are going to change completely and so on. And as a result, that scrubbing is going to find that there would be a mismatch over here, and that would find the problem very quickly. Yes.
Tell me the granularity of, do you check one instruction? Do you check?
That's a very good question. So we actually played with it, and so one of the things that in general, I will take your question one level up, and you will get your answer, I think. The issue is the following. So typically in fault tolerance, people would worry about performance and so on, which is not a big issue over here. The runtime of the test, per se, is not the biggest thing. The thing is the cutting down the debug time so that you can run more tests, right? So so one thing that we were worried about is, because if you do very fine-grained instrumentation, that whether we will run into the Heisenberg problem again, that the original, whatever the test was covering is not covered anymore, and as a result, we will have bugs that are not detected. Instead, what we found is so we never found a situation. This is interesting. So I always tell people that give us some challenging bugs. I can always come up with a pathological bug where QED will not be able to detect it, but the original test would, because you just have to create a different state machine that would kick something in, right? So, but that's not an interesting enough example. We never found a bug, and we have run like hundreds and hundreds of bugs by now. We have not found a bug that QED could not catch. But what we do is that we provide a knob basically, that if the user tells us that how deep their buffers are, the trace buffers are, from there we go and calculate. And and we try to keep the tests as less intrusive as possible by spreading out the error detection. So you have a trade-off between error detection latency and the intrusiveness. That's what we think where it has to go. But since I do not have a good example where QED was not catching the problem, I cannot exactly tell you that whether like how effective that is. Yes.
As a matter of deployment, do you expect the instrumented version to be the one that people use, or is it just for testing?
So I think the instrumented version people should be using for testing. For testing, I mean for validation, for pre-silicon verification and post-silicon validation.
That's not what will be sold on the market.
Yeah, it won't be sold in the market as that, because once you have validated, hopefully, once you have done a QED, you can say this is a good cheap QED, right? So that's what the hope is. By the way, so a lot of people were skeptical about, whether this thing would work for logic bugs. And here are some actually examples. So we have several hundreds of logic bugs from various companies. We are very, very fortunate that, they opened up their bug databases. And these were like actual difficult logic bugs, they call, that took a lot of, validation time. You see that the original tests, you have, tens of millions of cycles of error detection latencies versus, a few hundred cycles over here to find these bugs very quickly. And even there were situations of undetected bugs that would have been found by the QED very quickly. So, as so we had to go through this whole process to convince various companies that, this is a viable approach that, they could take advantage of. And now we are kind of in a situation where some of them are seriously thinking of deploying this in an actual, in an actual environment, to replace their tests with these tests. We'll see how that goes. So this is the bottom line of all this, that, so instead of running these very long tests, you run these very short tests, and, and as a result, you can do, good bug localization, especially, with multi-core chips, multi-core debugging, where, bug hops around and all that, that essentially is in some way, gets reduced to the problem of a single core debug, basically, because you found the problem where the problem has happened. So then the next question is, once you have, found the problem, what do you do about it? Right? So you still have to localize the bug, right? So here is a work that we did, which is called IFRA, where we were actually adding some very special recorders inside the chip. Now, as I told you, people already use recorders, which are like trace buffers inside the chip to capture information. Now, our trick was to use special recorders so that we don't need any failure reproduction, and we don't need any system simulation. And essentially what we were doing is that after the recorder contents were scanned out, this is when QED would tell that there is a problem. You do some post-analysis where you do self-consistency of the information that's captured in the recorders. And by doing that self-consistency analysis, we would go and do the diagnosis to be able to tell. In some sort, you can think of it as some sort of a tree, basically, a decision tree which says, did the bug happen over here or over there, and so on. And by doing this yes/no answers, we would go and nail down where the bug actually came from. I'm not going to get into the details of this at all, but I'm going to show you some results. So some of my Intel friends challenged me that whether we could show this working on their Nehalem architecture, which is their latest architecture. And my student actually went and spent time inside the company, and you can tell that 90% of the cases he could actually correctly localize what the problem was coming from, without having to do, again, any failure reproduction or any simulation or anything, which means that in real life, this would be much bigger. So what the Intel guys did is that they said, okay, we are injecting errors, and you do not know where I injected the errors, and let the system run, and the recorder is capturing information, and when you detect the problem, you look at the contents of the recorders and try to now do the debugging, basically using self-consistency analysis. What was found is that among this 90% of the cases, for 60% of the cases, you could exactly tell that this is the design block that the problem came from within this clock cycle. Versus for the remaining 40% of the cases, you could give roughly around 6 out of 270,000 candidates. Where does 270,000 come from? Well, this is a big design that has 270 design blocks. And since the recorders were 1,000 deep, so that's kind of the time-space amount that you can think about. And you can go and localize in that time space very precisely. So this was something very exciting that we found. And right now what we are working on is kind of to extend this whole methodology for big SoCs by taking advantage of QED. Any questions until now? So what I will do is that, I spent a lot of time on the complexity, and I knew that people will be asking questions. So next, I will talk very briefly about some of the CMOS reliability projects that we have, and then I will conclude. I have like another 10 minutes or something, right? Yeah. 10?
Maybe. Normally it's 5.
Normally it is 5. Yeah. I will try to wrap up fairly soon. Of course, I have a lot more slides. Okay, and so the thing that I wanted to show you is a couple things that we are doing in that space is
especially things that are going to make us crazy.
That's right.
So then you will ask questions.
Yes, absolutely. So for example, like if you have chips, you could have a cosmic ray coming in and flipping a bit inside the chip, essentially. Okay. Now you would be wondering what are the chances of that happening? Well, if you had a data center with a couple thousand processors running, and you were a banking establishment basically, you could have something like once every 30 days or something like that, you could have your bank account being messed up and you not knowing about it. So that's a very serious problem, right? And one of the classical ways of solving that problem is to put in a lot of hardware or software support inside a chip with a lot of redundancy to build in, fault-tolerant computing, basically. Only trouble is that, those are very expensive, and even for mid-range servers, you just do not cut into the market by using techniques like that. What we have been able to do is that we have these ideas called software resilience, built-in software resilience ideas that we are using to, cut down those costs while providing very high levels of resilience. We can cut down error rates by 2000x, as shown over here. And the way we do things is that we actually go and build chips. We do radiation measurements. Actually, there are facilities where you can bombard the chips with various particles. Otherwise, nobody's going to believe your results. Similarly, there are other problems, that one has to worry about, and I won't have time to talk about those. As I was talking about over here, if you look at chips, transistors, they're like human beings. They age over time, and the amount of aging of transistors depends on, whether the transistor was an assistant professor at Stanford, for example. And typically in the past, people used to deal with these problems by putting guard bands. They will say, okay, if this chip really runs at 1 gigahertz, I will sell this chip at 800 megahertz. Well, not that big, but they would literally put big guard bands and make the chips run. Now, those guard bands were okay because you had the so-called classical CMOS scaling. You are getting your chips faster, and then you keep adding a constant guard band. That's okay. But now, as you probably know, that the classical CMOS scaling, that you shrink a transistor and suddenly it gets faster, it consumes less energy and all that, that's gone. The only thing that's left is that you make the transistor smaller, they take less real estate, and that's it. And with that, those guard bands have started becoming very important. And so people have to figure out new ways of solving those problems. And the way we are addressing some of those problems, I'm skipping a lot of slides over here, is by using where we actually go and do physics. Actually, we essentially go and do device physics and try to find out what the heck goes on inside the transistors before they fail. And we try to find those device level signatures. And by taking those device level signatures, we abstract them out to the system. And then the system runs online self-test and diagnostics and all that, and discovers problems. And we can predict failures before actually errors show up in system data and state. So literally, we are building these systems where when some of these problems happen, the system will be able to tell, aha, I think within the next so many whatever, there is going to be a problem, and you better take corrective action of that. And we do some of that, basically. Yes?
I was wondering how general is your approach, your algorithms and mathematical framework? Obviously, you're very interested in the electronics and the CMOS, etc. I worked with software and power supply and networks, etc. Is your algorithm and kind of approach also applicable to other types of systems beyond electronics, which obviously is computing, which is obviously very important? I'm not.
No, I understand. That's
something I would be interested in.
That's a very good question. So I would say there are both aspects of each. In the sense that, so if I take, for example, my QED stuff that I was talking about right in the beginning, I think the basic principle of this error detection latency, I think, is something that's pretty much universal in some sense. Like for most of the problems, most of the difficult problems have that characteristic. And it essentially boils down to how you find the right assertion checks, as Anupam was talking about. And I think what the QED allows you to do is that it allows you to get around all that and run tests in a clever way. So if you have problems, so most of the difficult problems would be, there would be 20 events that would line up in some weird ways, and that would cause a problem. and after a very long time that would end up having this crash or something. I think that's fairly universal over systems, and if you use a QED kind of an algorithmic approach to deal with that problem, I think you will be able to do that. Similarly, in this whole robust system thing, in the reliability stuff, again, there are two aspects. One is, so we can be completely generic and completely, decoupled from electronics, and say, well, we'll deal with by redundancy and all that. The trouble is that then the cost becomes too high. As a result, we have to look for specific signatures that are from electronics. For example, as I was talking about, device physics level signatures that we look at. But at the same time, there are some very fundamental principles. This whole notion that we can predict failures I think, is a fairly generic notion. As long as you can provide signatures from the lower level, and that's where the application specific part comes in. This whole notion of running online self-test and diagnostics very efficiently, so that the rest of the system doesn't see much degradation, excuse me, performance. But at the same time, you're discovering failure signatures and telling when a system is going to fail before something fails. That's a fairly generic approach that one might use, in other systems as well. If you have some specific examples, I'll be happy to, talk more about it.
Great.
So, go ahead.
At that level, I kind of have this image still vague to me of experimental design, right? Automated experimental design.
That's right. That's right.
And I kind of want to think, well, where doesn't it work? And how do I know when to call up that, to pull that out of my quiver?
So that's the good part of electronic systems, right? So now, since we have so one of the things that electronic systems have done, the designers have done, is that we have very good models. That's what actually rescued this whole, how we design electronics, right? We have very good delay models, we have very good power models, now we are creating very good reliability failure models. And if you have good models, and that's where the application specific part comes in, then through expensive experimentation, design of experiments and all that, that how should you tune your system so that when you see certain of the signatures, you actually know that something is actually going to fail. I have a funny story about failure prediction in hard disks. I won't spend time talking about it here, but it's almost like that. So again, it's garbage in, garbage out. If you do not provide the right kind of information, you would be just calling home all the time. But there are interesting ways of getting around some of those problems. I would stop over here. We do a lot of work on beyond silicon CMOS, where we look at carbon nanotube transistors, and actually we have been able to build actual digital systems using carbon nanotube transistors. Even though when you grow carbon nanotubes, they look like a bowl of noodles, and so essentially it's about creating some sort of an order out of the whole chaos that's going on in the underlying substrate. But by playing games both in processing and in design, which was the key part over here, we could do clever layout designs that we could hide all those problems in the underlying substrate, and we could do that at a substantially low cost. Maybe you have an increase in overall area by less than 1% or even less than that. So nobody would even know that all those design tricks were going on in the underlying substrate, but still you would be able to solve those problems. So I would stop over here and take more questions and and have more discussion. So thank you very much for your attention.
Given the late hour,
sure.
I'm just going to ask the one question that came over the airwaves, which was I'm not even sure. Mayuri Kumarani asked, how can the QED find race conditions and timing-related issues?
Oh, actually, QED is very good at find race condition timing-related issues. That's something we found. Because what would happen is the following. Typical race conditions and timing-related issues that we have seen as bugs, and we have seen those, what would happen is that, so there will be 4 events that would line up. For example, if you were writing into the same cache line within X number of cycles within a certain specified address range, that's when we would have our timing race, and as a result, some of the coherency transitions will be delayed. That's a typical bug, and bugs are bugs. Interesting thing, we found that the same bugs are repeated in almost every company, okay, because these are human beings designing these chips. What would happen is that, so think about when QED runs, when the first request comes in, and let's say that those 20 events lined up, and as a result of that, you would see you would have the problem, but you wouldn't know about it. But the next time the same thing comes up, those chain of events have been broken, and things would just be fine. And as a result, the two memory locations where you're kind of writing the original and the shadow, for example, there would be a mismatch there, but still they will be sitting there. QED hasn't kind of kicked in yet. It's only one part of the QED that has kicked in until now. And then when you do, for example, the proactive loads and checks, which is almost like doing scrubbing on memories that I was answering Anupam about, that's when actually QED would go and say, oh, these are supposed to be the same and they're different, and I have found the problem. And that's how you found the problem within 100 cycles. Whoever asked the question, will be happy to show you a demo. But that was a perfect question because that was a very difficult bug that people had.
So thank you everyone for coming. Sorry to keep you a little late, and please join us out in the hallway for a little bit of cookies and soda. Thank you.
Thank you very much.